Welcome everyone back to the Multi-Agent Systems seminar series, which is organized by the Multi-Agent Systems Special Interest Group at the Alan Turing Institute. I'm just going to spend a couple of minutes, as always, to give you some background info, and then we'll hand over straight to today's speakers. So my name is Stefano Albrecht. I'm a lecturer at the University of Edinburgh, and I organize the group and the meetings jointly with Professor Michael Wooldridge from Oxford Uni. And basically, the idea behind this whole initiative is that multi-agent systems research is super important and very ubiquitous. It's happening in a lot of spaces. And the UK is one of the original large, sort of significant contributors in this space. But over the past years, I think the effort in this space has become quite fragmented, and it wasn't so clear anymore what was happening in the UK and who were the major labs and what were the opportunities. So based on this, we organized a seminar which took place in February 2020, and we had over 100 delegates from across the UK and Ireland, from the major labs and industry and university working in multi-agent systems research. So this was very successful. And following this, we started an online talk series, and today's one of the talks in the talk series. And we're also hoping to organize more in-person meetings in the future. But basically, the three main activities, just to give you some context, we organized a symposium. We're hoping to organize more of those in the future when the conditions are a bit more favorable. In the meantime, we have the online talk series. We, as a result of the first symposium, we also created an online virtual labs map where we try to pinpoint all the major labs and universities and industry in the UK. So if you have a lab that is active in multi-agent systems research and you'd like to be listed on this map, then just send an email to myself and Michael, and we'll add you to the map as well. So the map can be used to find collaborators as well, which I think is quite nice to have. And lastly, we have a mailing list which everyone is welcome to sign up to and send messages to for multi-agent systems relevant announcements, jobs, for example, meetings, and so on. And at the bottom of the slide, you can see our URL for the website where you can find all kinds of information. Lastly, we record all these online meetings and we put them up on our YouTube channel, which you can see here. And if you just go on YouTube and search for Turing Multi-Agent, you should be able to find our channel. So with that, I'm very pleased to announce today's speakers. Today we have Rory Greig and Freyr Arinbjarnar, sorry, complicated to pronounce for me, who are at Improbable, which is a UK-based company working on virtual environments, I think computer games as well, and they even have a defense element. So we're very happy to have you here to talk to us about the work you're doing. Thank you very much.
Thanks, Stefano. Okay, let me just see if I can. I think I'll just share my screen now.
Yes.
Okay, great. Oh, let me just go back. All right. Hi, everyone. I'm Rory, and I'm also joined by my colleague, Freyr. So I'm going to be talking about inverse generative social science, and Freyr is going to be covering some of the other activities that our research team do, and particularly our AI laboratory environment. So yeah, we'll go into details on these in a bit. So just to start off, as Stefano said, we're from Improbable. So you may have heard of Improbable before. We're a fairly large company now, but the main idea of Improbable is building massive virtual worlds. So we started off in gaming, so really giving game developers tools to build much more sophisticated, computationally intensive multiplayer games. And then in the past few years, we've been applying that outside of games for defense and government decision making. So this is kind of persistent virtual worlds for training and planning in defense. Basically, these are large-scale simulations of the real world with thousands or millions of agents and lots of different kind of subsystems of the world represented. So we're kind of modeling these complex real-world scenarios so we can game these out virtually for decision-making and also for training. So yeah, we're headquartered in London, and yeah, I think we're actually about around 1,000 employees now. So Freyr and I both work in the defense division in our research team. So we do a number of different activities in this team. We're still fairly small, but we are kind of growing. One of these is agent-based model calibration. So I'll cover, agent-based models a bit later if you haven't come across them. But the idea here is just kind of tuning agent-based models, making them more realistic, more accurate to real-world data. We're also looking at performance tools for agent-based models. So how can we make it easier for modelers to write models and have them run really quickly and efficiently, kind of using higher level languages like Python. We're looking at behavioral AI. So how can we make agents more realistic for these simulations, and also kind of a laboratory environment and tools to help people integrate and train AI, which Freyr is going to talk about. And so, yeah, with that, I'll hand over to Freyr. I think one thing I'll say is we're going to have time for Q&A at the end. So I think we can have like small clarification questions as we go along. But if you've got any larger questions, yeah, hopefully those can wait till the end. So yeah, over to you, Freyr.
Thank you. So next slide, please. My name is Freyr Arinbjarnar. You don't need to say that. So the topic that I'm talking to you now is to introduce our work on an AI laboratory that we've been designing and embedding within our platform toolset, our games toolsets. So the intention with this AI lab is to facilitate collaboration, so broad collaboration across industry, government, academia, and all sectors essentially. And as an example of what we are talking about and how we want to use it, I'm going to use a recent experiment that we did for the Army. We demonstrated far greater numbers based on the scavengers test, scav lab that the Games Department has recently produced. We combined different AIs, we switched different AI behaviors in the same scene, and so forth. So we are very keen, and the reason I'm giving this talk is that we are really very keen to find partners to work with in the future. Immediately to talk to. We are doing a lot of work now developing this and thinking it and designing it. And the more we hear from the community and the needs of the community, the better we will be able to meet the needs of the research community. So next slide, please. So what is the platform and the tool? So we have the ability to run a large-scale synthetic environment, a synthetic platform essentially, where you can plug and play all kinds of different systems into it. Live feeds, social media, all of the open source data, and we're developing pipelines to feed that in. We have, obviously the games unit that has expert in animation and texturing and making everything look very nicely in the UI, in the graphical UIs, Unreal Engine or Unity, etc. So we can harness, the powers of all of the different components that maybe lie outside the sphere of interest when you're doing academic research and are just looking at the algorithms. But we see a lot of value in being able to run our research within a very realistic environment to show the relevance of the algorithms to the actual environments and the actual problems that face the end user essentially, and the people that we think will use our algorithms. So next slide, please. So the example I'm using is the Army Warfighting experiment this year. And so this is the public challenge from MOD, from the Army. They need synthetics, realistic synthetics live that you can train with live and are responding to the actions of the soldiers and the events within their environment. They're especially interested in urban environments because they are complex. There's a lot of sensitivity. It's difficult to train live in real life within urban environments. So or among civilians, because obviously they don't have civilians, they just have soldiers. And they may hire actors or things like that, but that has limitations. So they're very, it would be very advantageous for them to have a very realistic urban training environment. And obviously what they want is they want the highest connectivity, exploit all existing systems and training and access and captures. They're open to using any current cutting edge or workable solutions that are out there. Next slide, please. And so for this, we spoke to many partners, and this is sort of the short list of that we integrated in this, throughout this experiment, into different things in different experiments. I will go into that. But essentially, we used both Unreal Engine for some experiment to visualize and VPS from Bohemia Interactive. We used SimCentric, that is sort of models for an application where you can model different things for army training and things like that. It's all geared towards the military. And we use their must fires, and we'll describe that, but that's essentially configured multiple fires on the enemy. And we use Discovery Machine, which have a very advanced AI. And all of these we could plug into and run on the cloud and run on our supercomputer, etc., etc. Next slide, please. So experiment 1 was about scale, and that's really not our work in defense research, but games unit research. Next slide, please. And so what is that? This is obviously the primary thing, is they want to large scale training exercises, whole regiments at the time, and across multiple modes and multiple domains and geographical location, etc., etc. And ScavLab from the games unit has proven that they can run 10,000 real-time users, and we replicated that experiment, all textures for the military, and the latency and bandwidth that is used is 1/50 of what you would without the Morpheus technology. Next slide, please. And with that technology, we could run simultaneously over 10,000 real-time synthesized player, and among them were soldiers playing a small squad of 10 people, of 10 soldiers. And you can see in the middle upper slide there, all of the synthesized soldiers there in a crowd, over 10,000 of them. And this is in a sort of simulated environment. It's actually 2 environments together. So there's an environment that we've designed specifically for the experiment, which is merged into a real geographical location that we took from open source maps. So we can do all kinds of merging and swapping together like that. Next slide, please. So experiment 2 is about really combining multiple partners, multiple modules, multiple technology into one. Next slide, please. And so what we did is we had VPS4 as the front end again. We took SimCentric Sapphires, and it's essentially you go into a Windows application and you set up a series of fires. So that can be aeroplanes flying over, dropping bombs. It can be artillery. It can even come from the Navy. It can also come from foot soldiers with, some sort of rocket launches. Any armaments really that can send fires and an enemy can be configured together. And what are must fires? Must fires is really when you have an officer who sees the enemy and he will call in to other sections within the squad, within the regiment, or even within other regiments, and request fires on the enemy, either to, it can be to suppress, it can be to show force over flee, it can be, you know, anything that the goal is. And this run essentially in a dynamic environment where you could configure fires live, you could set up new fires and have it executing sub-fires. During the simulation, we had a build to fight model, which sort of a probabilistic inference where with some probability, the soldier will either flee or continue fighting after he's been hit, or there's bombs falling nearby. And we did different kinds of configurations, which you can do through a website, and it's sent at the start of the simulation to set up the soldiers. So essentially, there's multiple fire events. You can select them live. They affect the dynamic. They can be multiple events. So the soldiers will change their mind on future events because there's a change situation. And they have individual beliefs. They are affected individually by the events. So they make their independent decisions. And we have a dashboard, web dashboard, which shows the analytics and all the information, messages, and everything that's sent between and published within the simulation. So you can run all kinds of analytical overview. And I will show you next slide, please. So here you can see the leftmost one is showing some of the web overview. You get a sort of timed graph going or plot going, so it sort of moves in time so that you can see how the effects have been changing over time. The middle one is top-down view in VPS4, where you can see the red dots are the enemy and the blue ones are your soldiers, and this is sort of looking on top, and there they are in place. And then you can see the bottom one, and it's quite small, but you can see the soldiers we have there have been grouped into sort of different squads. And so you can set parameters for the squad as well. And their bombs have fallen nearby. Some of them stand and fight. You can see some of the dots are there. Others have run away. And that is all shown in VPS. Next slide. Experiment 3 is swappable AI. So that is Discovery Machine, a US company that does very advanced AI, very complex, emergent. So they can run multiple civilians, which each civilian has a complex belief system. Belief system is culture and location specific. They're both generic actor roles, and there is also very specific down to specific traits of police, vendors, workers, specialized workers, localized farmers, from poppy farmer in Afghanistan to wheat farmer somewhere in Europe, etc. So they have a completely individual worldview, and they communicate and they make decisions within the simulation that is driven by the updates that are on the messages and interaction they've had with other agents within the simulation, etc. So it's been around for around 20 years. So we piped that through our systems and showed it in Unreal Engine with a engineering team from the games that did that. So it's a bit of an interesting thing. So the scene was an East European marketplace. So there's people dressed as East European or European, essentially, that had put up sort of a ad hoc marketplace among some apartment buildings. But the AI was for an Afghan population and then also for a Philippine population. You could swap those out, and you can also dial up and dial down the level of hostility of the civilian population towards the soldiers coming in. And the thing that we focused on was testing out the different types of culture-based reaction. So if in an Afghan population or a Muslim, primarily Muslim population, it is frequent that if you're a male, you can only talk to a male. You can't approach a female and start talking to her unless her husband has given some permission. But in the Philippine population, that is not a factor. And similarly, a female soldier is expected to talk to the females, isn't really expected to talk to males in a primarily Muslim population. So I'm going to show 3 video clips of this that show differences in behavior. So next slide, please. So this is a female trainee, a female soldier. It's just a configuration, you choose what you are. Approaching an Afghan population. And you see the male, he just walks, even though she's approaching, he just walks. They're not comfortable being approached by a woman. But this lady, when you come to her, she looked a bit angry, I know. But they are actually, this is just normal conversation gestures that are being displayed there. They're okay with talking to this soldier. And this was at a very short time that we had. So the textures are very similar, you can see that the same texture is used on multiple agents, but that's simply because this was a fairly local, this was unfunded and we had a short time. And that wasn't the emphasis of having rich textures. But if you can go to the next video, please. Now you have to go to the next video. I think this is the, now you got a male trainee in the same population. And now you see this gentleman will talk to him. If he goes to a female, she will walk away. And, see, and look at the men now. This one is starting to be angry. He's telling him to go away. They're starting to be not that happy about him coming, and approaching the women. And you can see at the end there, all the women have left the place because this is unacceptable behavior, and they simply get anxious and leave. That's just the culture. They leave the men to take care of this. So if you can go to the next video. And this is an Afghan population and a hostile crowd. I don't actually know if it's a male or female trainee. It doesn't really matter in this one. But you can see that they will all be fairly more hostile. So they're just walking away. This is probably a male. Just hurts all the women out of the marketplace. Yeah, and here you can see there's a group of men and they're all waving him to go away. And most everyone else has left. So this is really just a small example of the level of complexity and AI that they offer. And this is the main thing here is though that we are piping this through our system. You know, it can be affected by other things within our system, other modules plugged into it, like in experiment 2 we did, and demonstrated in different graphical user interfaces. Yeah, everyone is getting quite angry at them. So you see that how they've grouped together and they're just sort of blocking where the sortie goes, etc. And they all just decide to do this. Is all emergent behavior. But you can go to the next slide now, I think. So what is it that we are talking about? We are offering collaboration, and with anyone who's interested or sees reason to developing with us this laboratory, you know, and collaborate on research with us within it. And the thing that we are sort of building up and offering is a broad range of environments within each sector. So war games and milsim, obviously for our military, our defense customers, but also just for government and for industry, infrastructure and social networks and all that, you know, for climate change and things like that. And also to go into the games fan on you know, people that don't want to work on defense. We are also very interested in popular games and fantasy worlds and more collaboration with the games unit then rather than defense. And we offer interoperability, so we are developing multiple interfaces to, you know, extract, transform, load between our AI lab and other standards that are applied or bespoke interfaces that you may have, and translate that into our simulation and the messages from our simulation back out. And open and flexible to all kinds of suggestions there. But we also, you know, emphasize of, you know, aligning with mainstream standards to be able to give everyone access to mainstream algorithms, etc. And by doing that, we can give, you know, access to the mainstream, the cutting edge AI, the, you know, Google, you know, DeepMind algorithms, Microsoft, Unity, all of these big platforms that are offering algorithms, and also the environment. And once we have the, you know, when we have a good base like that, we can start extending the algorithms, combining them, etc. Next slide, please. And that's why we say we're standing on the shoulders of giants, because you know, we are building on the things that have been discovered to enhance what has been discovered and done by all of you guys. So there's access, so we are giving access, as I said, to a large range of algorithms, a large range of environments. There are an increasing availability of all kinds of different environments, all from, you know, advanced robotic environments, from DeepMind to, you know, board game environments, etc. And, you know, it would be interesting to hear from the community what kind of environment are the sort of priority. And this obviously, you know, being able to access this in one place allows us to do faster experimentation, develop new algorithms, improved versions of existing algorithms, and combine, you know, existing Apple together and different architectures, model structures, and compare it apple to apple rather than apple to oranges, as you often are if you're doing it sort of one implementation there and another in another place. Next slide, please. So, for example, if we think of the must fires in experiment 2, if we wanted to advance soldier behavior of the blue force, your guys that are coming in after the must fires, they typically advance under the must fires and then are in place to come down. Yeah, I'm getting pinged for time, so I'm just gonna. So in that situation, to model that, you would typically combine multiple things: hierarchical structures for all the logistics, A-star navigation, probabilistic inference, etc. And we can take, uniform logging of all of it, everything that's sent, and display it or store it for further analysis, etc. Next slide. And that's it. Yeah, Rory. Sorry for going over time.
No problem. All right, thanks very much, Freyr. So yeah, now moving on, we're running a bit behind schedule. I've got quite a few slides. I may go through some of them a bit quickly, but obviously we should have time for questions at the end, so happy to go back to anything. So yeah, this is kind of, I guess, moving away a bit from the specific defense applications and looking at just kind of more broadly at social science research. I want to just introduce an area called kind of inverse generative social science. So you possibly won't have come across this before, but I'll kind of explain what this means. And I'm going to talk a bit about a specific research project we've done, which is about learning agent behaviors for these multi-agent simulations directly from observed data. So the core idea of this is, what if we could take calibrating agent-based models one step further? So by Abm calibration, all I mean is tuning the parameters so that the simulation model fits data better. And instead of just tuning parameters, we actually learned the code of the model. So this is a research project we did about using genetic programming to learn symbolic code for agent-based models. It's a kind of flexible approach, which we showed by applying it to two different domains, opinion dynamics and bird flocking patterns. And we published a paper on this earlier this year at the Conference for Artificial Life. So what is inverse generative social science? So if you think of what generative social science, what this means is writing models of a social system comprised of lots of humans so that it recreates or can generate data that you've observed from the real world. And the motto of this is, if you didn't grow it, then you didn't explain it. Like, can you grow this phenomena? And that maybe will give you a clue to actually understanding the underlying mechanism there. So typically this would mean you would write a model, you would write the behavioral logic for your agents and then run all those agents together in an agent-based model. The inverse approach comes in when we say, well, what if we learned that model from the data directly rather than writing a model ourselves? So this is, you can think of this as a way to automatically select between different model hypotheses. So it's kind of automating that modeling process. And this is a kind of growing subfield of what IGSS. There's been 2 workshops on it. I also presented at the one this year. And there's been some kind of interesting papers on this recently as well. So again, just to recap, what is Abm calibration? This is just tuning the numerical parameters so that a model fits the data. Often this can be done with kind of black box optimization or kind of Bayesian approaches as well. So we're just tuning those parameters so that the model output reflects the real world data more. And this really was an experiment in going beyond just calibration. So can we actually learn the code itself for the model rather than just tuning parameter values? And just to be clear, this is the code for the agent update function. So in an agent-based model, you will kind of loop over all your agents and they will have some relatively simple behavior that each agent runs. And we're just learning that agent update function. And this then slots into a kind of manually coded agent-based model program, which loops over all the agents. So we're not learning the whole program end to end, because that'd be a really challenging search problem. And just as an aside, one thing that enables this is, again, the performance theme that I talked about earlier. We're looking at techniques for making models run really fast. This allows you to take millions of samples and run these models millions of times. And that turns out to be necessary for making this program synthesis kind of genetic program thing possible. So yeah, program synthesis, what do we mean by this? This is just broadly, how can you search for a program which fits a given requirement? Usually this is used as a domain-specific language because it's more constrained. Otherwise, the search space would just be too large. This is what is used in like Microsoft Excel, flash fill to kind of infer or induce kind of equations. And some of the challenges, this is really hard to scale. It's combinatorial search. It's a sparse search space. There's also a problem with bloat, where it learns kind of overcomplicated programs. But the benefits are that you get kind of interpretable models, or at least a lot more interpretable than just if you're training a neural network on the same data and you just have loads of neural network weights, which are kind of hard to even see what's going on. So the hope is that you actually have code that you can look at, and we'll see some examples of generated code. And then genetic programming is a subset of program synthesis. That's just doing program synthesis, but with genetic algorithms. So representing the program as some encoded genome. And so why do I think agent-based models are a particularly good target for this? Well, one of the core ideas in agent-based models is emergent complexity. You can have even very simple rules at the agent level can produce this kind of complex behavior when scaled to many agents. So, you know, an ant colony would be an example of this. Each ant is just doing fairly stupid, simple things, but the whole colony has this kind of complex intelligence. So what this means is the simple agent behaviors can be encoded with relatively few lines of code. So that's a much smaller search target and makes it a lot more tractable. So we can generate these complex emergent behaviors at the multi-agent level without having to synthesize really long, complex programs. And this project was an attempt to learn from scratch. So what we mean is we start with an empty agent update function. There's no kind of initial domain knowledge about the domain or priors in there. It's just an empty program, and the genetic algorithm has to fill that. And so this can hopefully avoid some human preconceptions about how these systems work, whatever systems it's learning from. Maybe this would give surprising counterintuitive results. And we're also using a larger, kind of more flexible domain-specific language than previous experiments. So again, domain-specific language, we just represent a behavior as a list of instructions. And these are all just kind of mathematical operators. So they're not like tailored to the domain. We'll see some examples in the next slide. It has some limited control flow. So there's if conditions. There are no loops, but it can branch with if conditions. And there's a finite number of basically memory registers that it can write to. And this is written, the DSL is written in Julia. So these are an example of some of the DSL operators we use. And again, you can see these are just like really basic kind of arithmetic or kind of mathematical functions or comparisons. There's nothing to do with like flocking or opinion dynamics in these DSL operators. So the genetic algorithm has to combine these in a way that will actually produce a model of the domain. And then, yeah, the mutation rules just need to be aware of the search space. This is just a feature of how the behaviors are encoded. I'm not going to go into too many details here. Again, the loss function. So we were actually targeting data generated from hand-coded reference models. So we kind of manually write a reference model, run it once to get some data from it, and then we relearn the program from scratch, just using that single trajectory from the reference model. And we're just kind of using the squared error between the learned model output and the reference model. So in some ways, this is just supervised learning. This is basically imitation learning, what we're doing here. And again, this actually probably won't go into many of the details here. This is just to say that we run the reference model, get some data, split it up into data pairs. We've got this DSL that is combined by the genetic algorithm to create a program. That candidate behavior is run for all of the data pairs, and then we just sum all the loss, basically. And that's the fitness function for the genetic algorithm. So another feature that we added, again, one of the key aims of IGSS is that we want to kind of learn new mechanisms about the domain. So we want the learned behavior to be interpretable. So how can we make these learned behaviors as simple as possible? So a technique we did here was, so the genetic algorithm sees the behavior as a linear list of instructions. What we did was convert that to a computational graph, and then it's easier to apply automatic simplifications to that, like removing redundant operations that don't affect the output. We can pre-compute some constant terms that don't depend on the inputs. And then we can output hopefully simplified valid Julia code that you could then take and run, or just look at to kind of see what's going on. And I'll show you some examples of the raw and simplified code. Okay, so like I said, we did this in two different domains, bird flocking and opinion dynamics. So let's kind of look at what happened. Again, just as a refresher, you may have come across the Boyd's model before. This is our reference flocking model. So each bird is just following very simple rules like alignment. So kind of align your velocity to similar to nearby birds. Cohesion, kind of steer towards the center of the group. Separation, just avoid getting too close or colliding. There's also one other feature of our reference model, and this is relevant because we're going to look at how the learned training process kind of learns all these features. That is just normalization. So we normalize the velocity so it has a constant magnitude. So they're all moving in varying directions, but at the same speed. And again, just to show kind of how this learned function fits into the ABM program. So we've got a for loop that loops over all the agents. This steer behavior is the function that calculates the new velocity at every time step for every agent. This is the bit that we're synthesizing and kind of learning from scratch. So that starts empty. And then we just have a simple move function, which is hand-coded. That just takes the new velocity and applies it to the position. That's just kind of really simple physics. That's nothing really to do with the domain necessarily. It's just something that we can hand code and make it a little bit easier for the training process. Okay, so here are the results. I mean, what we can see here is just that it achieves a very low loss. This kind of reduces nicely over the training run. Note that it does take millions of kind of executions of the loss function, but just knowing that it has a low loss doesn't tell us too much. We also want to look at actually the output and the performance of what that looks like subjectively. And so here, this is plotted side by side, the reference behavior on the left and the best learned behavior on the right from a training run. This is just a way to like show the trails of movement of the birds. So you can kind of see this flocking movement on a 2D still image. And you can see like, you know, these are not identical because it is a chaotic system. So they're not going to be like bird for bird exactly the same, but you can see very similar patterns of kind of clumping together, kind of circular patterns of flocking that we want to see. And that's maybe even clearer if we look at the videos. So again, reference model on the left, synthesized model on the right. They're not identical, but you know, subjectively, these are very similar. If we didn't have the labels, it would kind of not be clear which is the learned one and which is the handwritten one. So starting from scratch, this has recreated the behaviors of the domain, you know, in a satisfactory way, which is a good result here. And so just to show kind of how this evolves over time, I kind of plotted snapshots of the flocking movement as it goes. And you can see at the start, they just kind of fly off in random velocities and random directions. And over time, they kind of cluster together a bit more and eventually have these kind of circular flocking patterns, as you'll see at the end. Cool. So I'm just, yeah, so you can see these now kind of moving around. I'm just going to hurry on because we're running a bit short of time. And again, this is just kind of plotting some of that on the loss plot. So you can see some large drops in loss correspond to it learning specific kind of features. And this is a kind of property that, you know, we have the generated code to look at, so we can kind of look at what's going on here. We can also look at the output for these intermediate forms and kind of see in what order and where it learns these functions. So here it kind of learns to normalize the velocity. This big jump corresponds to learning cohesion, where it kind of moves towards the center of a large group, which causes these kind of swirling flocking patterns. And just to look at the generated code, so this is the code for the reference model. Obviously, this also has kind of nice interpretable variables because it was written by a human. And then here is a raw generated code. So this is before we've simplified it. Again, you know, it's not huge. This is probably easier to look at than like neural network weights, but it's also not the most interpretable. I mean, it would take a while to kind of go through and parse what's going on here. It's not helped by the fact that we can only have one mathematical operation per line, really. But we then automatically simplified this by doing this process of converting it to a computational graph and simplifying it and then printing out this function. So this is kind of completely automatically simplified. Again, you know, maybe it's not completely interpretable as if it was written by a human, but we can go through and see that, you know, this is just a linear combination of all the inputs. This final line, which says kind of normalize the sum and then multiply it by basically a magnitude of 5 or 4.999. If I go back, you can see in the reference model, this is basically exactly the kind of same logic. So even just at a first glance, we can kind of pick out some things that are the same. And if we go through and look at it for a while, we can kind of see what's going on here. We could rearrange these lines a bit more, for example. And then kind of, yeah, just opinion dynamics. I'll kind of breeze through these. This was a kind of opinion model. So all agents have an opinion between 0 and 1. Agents are randomly chosen to interact. If their opinions are within a threshold of each other, then they become even closer together. So this is a kind of homophily model saying that if you're already close in opinion, you will become even closer. So we're trying to relearn this. This is the kind of pseudocode here. Again, we achieve a low loss. And if you look at the output, you can see, you know, these are actually almost identical. So this is the reference on the left, the learned behavior on the right. What you're seeing here is all the agents are initialized with random opinions, and then they gradually form these clusters as they get closer together. And the learned behavior has definitely recreated this. You can see almost exactly the same clusters here. We can look at the code. The raw code for this is arguably even more complicated. We also require some if conditions here. And then looking at the simplified code, it's still a bit complicated, but I was able to pick out some kind of interesting stuff going on here. So again, the first line, it's just getting a difference of these opinions. It's kind of calculating the square of those and then the square of the square, so the power of 4. And it turns out it's basically doing a polynomial function of the difference of opinions. I've plotted this here, and wherever this polynomial evaluates to less than 0.001, this condition is true, and it executes this code, which corresponds to updating the opinions. So I wouldn't worry too much about the details here, except just to know that this is a polynomial and it's got some conditional logic. And it turns out the value of the threshold for this polynomial kind of is where the difference in opinions is below 0.2. And the value D for the threshold I used here was exactly 0.2. So it's recreated this logic in a slightly different way, but the logic is equivalent. And again, we can see how this kind of goes through the loss plot. It learns the polynomial condition here, and you can see how it starts to form these clusters. So yeah, just I want to leave some time for questions, so I'll just go through this discussion. But yeah, so in terms of interpretability, it still can be a challenge. We can interpret it. It's not necessarily trivial, but the automatic simplification helps a lot. The next step is an experiment we're running at the moment where we actually have a complexity penalty term in the loss function, which is related to the length of the program. So that's to try and incentivize it to learn as short programs as possible. And just for future work, I think we really want to apply this to real world data, which also means we're currently kind of testing the robustness to noise, because we're using perfect data, which was generated at the moment, whereas real world data would have noise. How can we retain interpretability when we get to more complex learned models? And then another interesting thing would be heterogeneous agents. So right now we're just learning the same update function for every agent in the model, but we can say maybe there are different types of agents that are going to learn different logic. And yeah, so just to summarize, we've kind of successfully synthesized ABM logic from scratch with genetic programming in different domains. We've shown that you can interpret that resulting code, and you can manipulate the computational graph to kind of automatically simplify it as well. So yeah, that's the end of both of our presentations. So yeah, I'm not sure the best way to do Q&A, but we still got just under 10 minutes for that. So I guess if you have questions I can redirect them to either me or Freyr.
Yeah, thank you very much, Rory and Freyr, for your very interesting presentation. We do have a few more minutes left, so handing over to the audience. If there are any questions, please just feel free to unmute yourself and go ahead.
Hi, can you hear me?
Yes.
Yeah.
Hi, I'll just start to get things rolling. I'm Max, and so I'm working for Waymo, but kind of question is unrelated. But I was just wondering what you think was the biggest challenge in getting those models to work the way they did? What was the biggest bottleneck you had to solve?
Yeah, that's a great question. I think the biggest challenge was the performance aspect. So like you saw there, so we had like fairly limited computational budget, and it does require kind of tens of millions of evaluations of this loss function. So like basically, yeah. So there's like a very limited time we have for each kind of loss function evaluation. And typically and that involves executing the learned behavior. So each evaluation of the loss function involves executing the behavior for every single data point. And we're using maybe, thousands of data points just to evaluate the loss function. So yeah, what that means is just a lot of kind of optimization, kind of learning some various quirks of Julia to make sure that we can get this executing as fast as possible. I think the other challenge is more a general problem of using genetic algorithms of like making sure diversity is preserved. So we're using kind of multiple population pools. There can be problems of like premature convergence. So this was more a problem with the opinion dynamics one. So sometimes it doesn't always converge. Sometimes it does get stuck in a local minima. So we're still exploring various ways in which we can kind of measure the diversity of the pools and also like make sure we kind of preserve that diversity as well. So I think that's, as we scale up to more complex models, that is definitely, I think, going to be the biggest challenge. But yeah, great question. Thank you.
Okay, I see a few people. So thanks for the question. I'm seeing a few people raise their hands, so I'm just going to go in order. First one, I think, is Orawa.
Hi there. That was great. That was really interesting. I love both parts of it. I've got sort of two questions. So the first one is, one of the challenges that I'm curious how this presented. So the map between individual behaviors and emergent outcomes is very much not continuous. It's very, very not smooth. And it's particularly subject to things like phase transitions. So are there ever any kind of challenges with things like a mode collapse where you're kind of stuck in one part of the simulation space where you can't escape because it's, these kind of systems are very susceptible to those kind of like quite massive discontinuous changes in behavior. And sort of a second question is around why symbolic logic, like specifically, because I mean, a lot of what you're describing could also possibly re-expressed as sort of function learning or like let's say a convolution kernel or a graph neural network could describe some of this behavior, right? And then you could, implement this in message passing as well. So was there a specific reason you chose sort of a symbolic approach to this?
Yeah, so yeah, two really good questions there. So the first one in terms of like, phase transitions and this kind of really highly nonlinear behavior, that is typical of agent-based models. I think, one thing is I would imagine genetic algorithms are maybe a little bit more robust to that if you can tune them correctly. But I mean, I think it was, maybe we just got fortunate with these two models that the search space clearly it was able to navigate them, but I imagine there could be some like really massive discontinuities. So I guess it'd be interesting kind of digging in a bit more like what does that kind of lost surface look like? Because even very small changes in symbolic logic could lead to like very large changes. Even if you weren't doing this kind of running it for multiple agents and this sort of emergent ABM effect, even just for a single program, a small change in logic can obviously cause like a huge change in output. It's not like that smooth necessarily.
Well, for the diffuent model, like even like a move from a quadratic to a cubic function will change it drastically because it'll end up converging versus having like a push away as well. So there's like a lot of very big changes that can happen, very small changes in your user behavior.
Yeah, absolutely. And I think that is one of the reasons it does get liable to get stuck in local minima some of the times. It's like still the minority of training runs get stuck, but perhaps it just gets into something that's quite good and any change would actually make it much worse. And yeah, just in the interest of time to answer your second question. So the symbolic logic, again, it really comes down to this idea of interpretability and inverse generative social science. I guess we're trying to learn, in theory, if you could just feed this data from a domain, this could uncover mechanisms that you can actually interpret and kind of look at the logic because it's like, limited constrained logic, we're limiting it to like 30 lines of code or whatever. And I think you could definitely use other function learning techniques like a neural network or, I've actually seen instances of trying to learn flocking models with graph neural networks and message passing. I think those would be really interesting to explore and contrast. But I think you then get the problem that you just have loads of neural network weights that are just hard to really dig into and know what's going on. And I guess there's like neural network interpretability work too. So definitely an interesting area to explore. I mean, I think here is just the idea of one, would this even work? And then also it has the benefit of shorter kind of interpretable logic.
Okay.
Thanks very much.
Thanks for the question. Next one is Ian Sheridan.
So very good, both of you. Can you hear me okay?
Yep,
yes.
Can you hear you fine?
So starting Freyr, I was intrigued with what you're doing. Obviously, it has many applications. My specialism is navigation, especially GNSS, so GPS and other systems. And I've looked at that in some depth in the context of drones. But looking at your military context, something that is very obvious, but I'm trying to put it in short form. If you imagine on one extreme, in terms of competency, you have an orienteer athlete, someone who's very good at orienteering. Most people struggle with navigation. They probably struggle even more now because of, as we know, there's a sort of loss of sense of direction because of GPS and equivalents on smartphones. So that is very much, in my opinion, a fruitful area to explore with any armed services. So very briefly, you can imagine someone is using GPS in an urban environment. If that cuts out, which often it will for various reasons, particularly tall buildings, you want that combatant or peacekeeper to know quickly where they are. So they have to have the flexibility of mind to switch from using cutting edge technologies, which is all very sensible, including calling in fire, but then going in effect blind, being able to quickly say, okay, I'm back to paper map, compass, and my own nous. I'm sending you a book. He's a Harvard academic, very smart scientist, Huff, The Lost Art of Finding Our Way. Have a good look at that. That will give you many fruitful ideas. Not least, he talks about how people get lost. And when someone gets lost, even a very good map reader, you go round in circles. This is proven when they find people in jungles. They tend to sort of go around for days, sadly. Anyway, that's that. Yeah. Over to Rory. You speak very quickly. I would really urge you to slow all that down, because if you're in front of Sonny or an armed service, they might think you're brilliant, but they'll never find out because you're going through at a rate of knots. I know you had limited time, but really watch that. There's me speaking very quickly, but it's because I don't want Stefano to tell me off. So your murmuration, what struck me is what's missing or what's next. And it's this, that I could see, and I'm just floating ideas, a project that looks at, well, what do they do next, having groups, or if the temperature changes, at what point do they all learn to disperse? If one reason is that they're grouping to keep warm, whatever, I appreciate it's several reasons. Or another might be very relevant to a crossover with humans. What happens if some of them get injured? What do you do then? Are there some signals if some are injured, you should just completely regroup? So that adding in this sort of extra, I hesitate to use randomness, but the change from grouping to murmuration, what triggers it, and how they learn that must be an extremely fruitful area for you, in my view.
Yeah, absolutely. I think those are great ideas. I mean, particularly, incorporating more sort of environmental or contextual data. And also another thing we want to do is, kind of state on the agents themselves. So right now, they're all kind of homogenous, but if they had their own kind of latent state that they could update and then kind of do some conditional logic on, I think that would make them able to learn much more complex kind of realistic behaviors like that. So yeah, absolutely. I think those are really great ideas.
Thank you for your recommendation and observation. It's very apt, because part of the warfare is that, their equipment can be cancelled out. There are techniques to, nullify electronic equipment and messages back and forth, so they can be, that's one of the threats that they have, that they can be, cut off from others within their regiment or squad or anything, so they can be completely stranded, and they need to train for that.
If you go down to -10, smartphones and all the GPS devices, they can easily all cut out, then you are in trouble, because you.
I have trouble already.
It's even worse because it's so easy to use a smartphone. So you explaining, I'm the guy who, I'm giving you this AI, but I'm making sure you can all do this analog by learning how to switch between the two, and it will be on a very random basis, because it's often when something malfunctions. Well, thank you.
I've copied down the name of the book. I'm gonna look at it. Thank you.
Okay, thank you. And I think we have one more question lined up from Joel Dyer.
Hi, can you hear me?
Yes.
Yep. Hey, Joel.
Hey, Rory. Nice talk. Really cool stuff. I just wanted to ask a quick question about whether you're thinking about any ways to sort of incorporate prior information on sort of the space of behaviors that you're willing to learn for the agents, because it seems that you might, if you're thinking about opinion dynamics and things like that, you might want to incorporate findings from behavioral science and psychology and things like that.
I think that's a great question. It really kind of cuts to the heart of this, like, what are we doing with IGSS? So the way I see it is, like, there's this kind of spectrum of, like, on the one hand side is what we're trying to do, like, from scratch, of like no kind of priors and just basic mathematical operators. I don't know if that's necessarily even the most useful way, but it's just kind of to show that that's even possible. And I think the other end of the spectrum would just be like completely manually coding it yourself and not learning anything. I think in the middle is like definitely the most fruitful area. So I think there's a number of ways that you can inject those kind of prior kind of restrictions. So one would just be the choice of operators and how you set up the DSL. So like maybe you could include functions which are not just mathematical primitives, but things which actually have some meaning in the context of opinion dynamics or something like that. And then it's just like reconfiguring those. I think the other would be I mean, I guess there's other things you can. So I had like some of the logic was hand coded, and then we're learning this like function that slots in from scratch. So you can add, you can sort of mix and match. This is a cool thing about program synthesis, is you can like just sort of leave a hole in your program of the bit that you don't know, code the bits that you do know or have some opinions about, and then it will learn, kind of fill in the blanks. And so I think there's quite a like productive opportunity there to just combine prior domain knowledge, and then for the bits that we don't know, just say, oh, let's just learn that. So yeah, great question.
Cool, thanks, Rory. Good to see you.
Okay, so thank you very much again to the speakers. Really good presentation, and also everyone asking questions. So this concludes the multi-agent systems talk today, and we have more talks lined up in the coming months. So have a good rest of the week, and hope to see you again at the next presentation. Thank you again to the speakers, and see you soon.
Thanks.